Okay, well, good afternoon everybody. You'll see the title of the talk as it ended up in the programme is a bit of a giveaway, and I'm going to be talking about two things. One is SKYLON, the other is a little bit more mundane but maybe of more immediate interest. Let's start with SKYLON because everything starts with that. SKYLON is a space plane. It takes off from the runway. Indeed, it is the runway that's giving Sally such terrible problems because we're the one that wants the very high strength, very long runway. It goes into orbit, delivering about 15 tons, and it then comes back and glides for a runway landing, and the point there is it is reusable. Now, being reusable, we then hope that we will reduce the cost, we'll improve the reliability, and we will speed up the availability by considerable degrees. Now, the numbers I put up here are what is proven in the 400 test flight program. The actual underlying vehicle's achievable reliabilities and turnaround times and the number of flights are things that we will find out when it becomes operational. But when you buy a SKYLON from us after the test flight program, that is what we will have proven it will do. Now, of course, we would all love a vehicle like this, and after 50 years of space flight, the question is, why haven't we got it or anything even halfway close to it? Well, one of the key things you need is a special piece of technology to do it, and that is the Sabre engine, which is basically what our company is doing. Indeed, we've just had 60 million promised from the government if we can find a lot of other money to help that process along. And so I've got, again, just slightly contradict Sally a little bit. SKYLON, although it's orbital, desperately needs the output of that study because we are about to design the engine. And if we don't know the certification requirements, that's going to be a difficult process. Anyway, I thought at this point I would hand over to somebody far more authoritative than me to explain SKYLON and in the context of what it might mean to you in the microgravity and space environments community.
This is the SKYLON personnel and logistics module, which carries people and cargo into space and delivers them to orbiting facilities such as the International Space Station. Here the module is configured to carry 8 station crew members and 2 tons of supplies and equipment. It is carried by SKYLON, an aircraft-like spaceplane projected to be operational before 2020. The module is loaded into the payload bay like any other payload, and SKYLON can carry the module without any special modifications. SKYLON reaches space using 2 hydrogen-fueled Sabre engines. These breathe the air from the atmosphere until they reach a velocity of 5 times the speed of sound and a height of 26 kilometers. Then the Sabres convert to pure rocket engines, burning liquid oxygen and liquid hydrogen, and power the spaceplane into orbit. Once in orbit, the payload bay doors open, and SKYLON performs the maneuvers that will take it to a rendezvous with the space station. The passengers and crew will be more than 40 times safer than in current crew delivery systems. The International Space Station has housed people in orbit since 2000 and is expected to remain in operation until at least 2020. SKYLON could fly servicing missions during its development program and then enable the space station to be refurbished and serviced for an extended life beyond 2020. It attaches at the same place as the space shuttle and will replace all the capability lost when the shuttle fleet is retired, but at a quarter of the price. We have begun to contemplate our origins. It is said that we are the children of stardust, and now is the time to realize our destiny. SKYLON could enable the International Space Station to fully realize its potential as the foundation for human presence in space.
many people can say they've directed Brian Blessed on their CV. The video is a few years old now. SKYLON has slipped to the right a little bit. We're now looking probably at about 2023 for operations and first flights in 2020. But then on the other hand, it looks like the space station may have its life extended to 2025. So we may still have a situation where SKYLON is actually arriving at the International Space Station. However, never mind that. In the longer term, what would SKYLON mean to microgravity and human spaceflight? And I think the first thing is the lower cost. Now, the lower cost doesn't just affect the cost of reaching orbit, it also affects the cost of the things you put into orbit. As an example, this this space station here was part of a study we did to check SKYLON's capabilities to make space stations. This one clocked in at about $1 billion acquisition cost, including the launch. So for $1 billion, you have a working space station in orbit. The operational running costs of this space station were around 100 million, a little over 100 million a year. Now, those numbers may be a little optimistic, but they give you the sort of order of magnitude that you would have. The space station itself is a 4-man station, but is about a quarter to a fifth an ISS for that matter. So the general costs are coming down. The next thing that happens is SKYLON, if it's configured, not as shown in the video, but configured as a passenger carrier, can probably carry about 24 people or in that order. That means with the lowering of costs that it may be, in fact I suspect and hope, it would be easier to send the researcher up there to do the experiment than to have the astronaut do it by proxy, and end up far more in the sort of situation we have with zero-G flights currently, that there's experts on hand to help you work the system in the new environment, but basically you do your own research at the station. And the third important thing is because the capacity is much smaller, the costs are much lower, it will be easier and quicker to turn those researchers that do have potential, either medical or social potentials or commercial potentials, to turn those potentials into reality thereafter. So I think the impact on the sort of work we would all have to do would be absolutely immense. That would be the whole point of doing it. But before we get our SKYLON, we have to get our Sabre engine. And vaguely, quickly how it works, air goes in through an intake, that bit's kind of obvious I guess, and it's compressed here by 150 times, taking it to the pressures that are needed to force it into a rocket engine combustion chamber. Now the problem we have is the air here at Mach 5 is about 1,000 degrees, and we want to compress it by 150 times. If you remember your physics, that's going to get very, very hot indeed. So the way we resolve that is we put it through a pre-cooler, making the fact that the air here is almost liquid. We take it just short of the point where it starts to liquefy. In doing so, we take 400 megawatts out of the air and put it into a helium loop that is a sort of continuous loop going around. It's made cold by the hydrogen ultimately. So here it's made cold at liquid hydrogen temperatures, here it's made very hot by cooling the air, and the energy that we've taken out is the energy that is powering the pumps and the turbo compressors. So we don't lose the energy we've taken out of the air, it becomes part of the engine cycle. When we want to go rocket, that top line is taken out, and this heat exchanger here with a pre-burner now powers the helium loop, and it's just a variation on what's called stage combustion rocket engine cycle. So it's just a very efficient hydrogen-oxygen engine. Now the intakes, the compressors, the pumps, the rocket engine chambers, even pre-burners, and this sort of heat exchanger are things that already exist in rockets and jet engines. You may argue that, well, hang on a second, you're not using them in quite the same way that they're being used in rockets and jet engines. Okay, we say we've done an awful lot of work checking those existing technologies in the new application we have for the Sabre engine. What is new and not being done before are particularly all the heat exchangers, but particularly this pre-cooler heat exchanger. Now a 400 megawatt heat exchanger, there's two in each of the Nimitz class aircraft carriers. There's one in the sort of average power station, that's the sort of power station of power, and they weigh between 50 and 100 tons. Obviously that ain't going to go anywhere near the air, let alone space. What we've been doing at Reaction Engines is, and this has been the bulk of our activity, is making heat exchangers that can do that 400 megawatts for 1.25 tons. So it's a massive change in the technology of heat exchangers and what they weigh to do a job. Here is the test heat exchanger that we have produced. Basically, the heat exchanger itself is this thing in the middle. To get enough air into the Viper jet engine, we have these two dummies either side, so there is enough air intake for the jet engine. This looks like an air intake, very deceptive, it isn't actually blocked off. The air actually comes in sucked in through the sides of the cylinder, which you will be able to see when this video gets going. This is looking inside the heat exchanger during a run, and you can see the air coming in. The heat exchanger is this sort of bird cage effect, partly blocked off, and you can see it's running for more than 3 seconds, and if we didn't have our frost control system it would have blocked up in 3 seconds. So there's proof for seeing it that we can control the frost formation. There is this sort of cloud. This is, you can see the air also coming in from the dummy in front of the heat exchanger. It's the warm wet air coming in here meeting the very, very cold air from the heat exchanger that's creating that cloud as it gets sucked down into the jet engine. Now, we've run this thing about 500 times, and not all of them deep pre-cooled, but we've done enough that we know that the 200 runs that we would need in a flight engine I've done. I should point out this is not a laboratory demo level. The modules and things that this is constructed from are the right size, and the technology, well, we hope to do a little better, but pinch come to shove, we could use this technology on the flight vehicle. So, we're covered here. We're ready to go on the main engine development with all these technologies in place. Well, except we do have an outstanding interest in advanced nozzles. And we're not yet certain whether we will put these on the final engine or not. These are called ED nozzles, and you can see two of them here. Not terribly clear what's going on, but basically we're putting a plug down the middle of the throat of the rocket, so that instead of forming a column of gas out of the exhaust, we create a tube of gas coming out of the exhaust. And the centre of that tube is open to the atmosphere and will adjust, so the thickness of the tube adjusts as the atmosphere pressure changes, and it automatically adjusts to the change in atmospheric pressure, producing an optimum rocket for any external pressure. Sounds very good. I can tell you, if you get into it, it ain't as simple as that, not by a long way, but they are of interest to us still, and we are working. You see here two of the test engines. There's been a couple after that, and we're about to do another one called Stoic under ESA direction. So we're really interested in these ED nozzles. I thought I'd show you an ED nozzle firing. In fact, I'm going to show you a strict firing. It's going to happen rather quickly because these don't have any cooling, so the maximum time they can run is about half a second. That's quite enough to tell you what the flow is. It's essentially static as far as knowing what the flow conditions in a rocket are, but in that time they go up to 300 degrees, and the copper is getting a bit sort of, don't like it anymore, so we switch off and wait 2.5 hours while it cools down, then to do the next run, which on a hot summer day is rather pleasant, unless you're one of the nerds who goes around and looks at the results. Okay, so, as I say, don't blink or you miss it, but here we are. This is done at our test site at Westcott. Right, doesn't really give the impression of the noise. The previous one, Stern, we had someone about a mile away with a dB meter and he read over 100 dB. So we tested Stern in a nuclear bunker. Sorry, we were in the nuclear bunker and the Stern engine was just outside. But occasionally we didn't close the blast doors. People sometimes, instead of watching the monitors, went just to get the experience by the blast door, and it always came back white and shaky. So, that's why we'll be having SKYLON in very underpopulated areas. Now, of course, the problem with these is they're, as the name suggests, they're static. It's sitting in one atmospheric pressure and it isn't moving. And in the flight vehicle, the atmospheric pressure is going to change and the air is going to be flashing past and up to Mach 5. In fact, even maybe a little bit longer. So what we now want to do is to test these nozzles in changing pressure and with supersonic airflows going on the outside. And the only way we can think we can do that is by actually doing a flight rocket with that sort of nozzle in the exhaust. So Valkyrie is Alan doesn't like me calling it a sounding rocket. It's a rocket that goes up, and the engine at the back has one of these nozzles all instrumented up, and we will fly it. And we've managed to match the Mach number altitude profile, that's the speed against altitude and therefore back pressure, to better than 10% of the SKYLON ascent. So this will be a very accurate representation of what the nozzle will see during a SKYLON type ascent. We've got some really weird propellants, ammonia and nitrous oxide, and liquid hydrogen, which barely counts as a propellant given it's got no chemical capability, but it's in the mix. And the idea is that those actually create an exhaust product gas that matches the air hydrogen we use in the stern strips and all our test engines on the ground. It also matches the exhaust products of the Sabre engine in air-breathing mode. So that's why that's been selected. The downside of that is that it is not a good combination and it's not very good performing. In a study that was done for the UK Space Agency at the spaceport, and I've got to say your guys on the CAA who are studying that have had all the work pretty much done for them by a study that was run by SSTL, which I believe they've handed the results over to. During that study, of which we were a part, we were pooling what technologies we had. We were trying to assess what technologies were in the UK for launcher activities. So we came clean and said, well, we are doing Valkyrie, and in fact we're hoping to have Valkyrie launched sometime late next year. We're already doing things like developing the tanks and the engines and everything, so it's a program already well on its way. It's not just a quick paper study. So we owned up to it and said, okay, guys, come clean, confidential for the moment, we're doing this Valkyrie thing. And we were also getting an indication there may be a market for sounding rockets out of the market study. And somebody said, well, can't this be a sounding rocket? And I said, well, no, because it doesn't have a payload. We've got such wretchedly awful propellants, there isn't any margin to put a payload on board. But I said, I'll tell you what I will do, is I'll look at what happens if we change the propellants. And so we ended up with this thing, VDSR, which just means Valkyrie design. It's not a proper name for it yet. And it is changing the propellants to LOX and kerosene, but keeping the other systems the same. And that produced a sounding rocket, potentially, which has got about a 10 to 20 kilogram payload and can take it up to about 150 kilometers, which is very similar to the petrol sounding rocket that we stopped using in the 1980s, which has an almost identical performance. So the question then arose is there an interest in this sort of system, given we can probably produce them for a flight cost between £100,000 and £200,000 per flight campaign. To be honest, probably more towards the 200,000. And that's one of the reasons for coming here today, is to ask you that question. If this was of interest, we could move things forward to make a vehicle like this available. So do let me know if that is the case. I might point out that if you do say there's an interest, I might just check that it wouldn't be easy to do it with solids. We don't necessarily do it that way. It's just been triggered as something which does seem to be a hole that people might actually want to use the facilities that were available. With that, I'll say thank you.
Thank you very much, Mark. I didn't give a Q&A opportunity to Sally, but I thought it would be useful if we just did a quick Q&A if we've got any questions for the two of you, if that's all right, now, because it's quite an appropriate way to finish the formal part of the conference today, looking at the future, looking at commercial spaceflight with a very particular UK emphasis. And any questions, any thoughts or statements, or any requests for Mark's capabilities and sounding rockets?
Mark, you mentioned about using a strict or stern-derived rocket to achieve better altitude performance. Are you able to say how you're overcoming some of the problems with using a conventional nozzle from atmospheric normal pressure to to the vacuum in space. Is that something you can comment on?
Yes, although it's not necessarily very interested in everybody else in the audience, but basically there is a problem with nozzles where you try and expand the gas to well below atmospheric pressure in order to get the performance at high altitudes. They do something called separate, which can be very nasty indeed. There's a lot of mythology about that. And in the UK, by accident, there was a lot of work done in the 50s that meant we knew you could do it, work that we've confirmed in the University of Bristol. So we know how to over-expand these nozzles safely, but you do get a performance loss because the atmospheric gas, the gas that you're creating in the exhaust is less than atmospheric pressure. Essentially, you have a suction effect on the back of the engine, which is not good news. And if we could get rid of that suction effect, we could shorten the runway, which would obviously help Sally's people a lot. We seem to be 12.5 kilometres, obviously, given the collywobbles. And the other thing that we can do is maybe get half a tonne of payload. That's if it worked perfectly. We know it worked, and I can't really tell you how, just because we don't precisely know yet how much we get out of it. But we could use conventional nozzles if we had to.
And a question more for Sally. Are there any idea of where such a spaceport might be positioned in the UK?
Yeah, but it's James history. You said it, not me. There are a few ideas. Clearly, they're going to have to be coastal. There's one possibility would be for the SKYLON that would be inland, but you only have to think about population density in the UK to know that it's got to be coastal. You're going to be, certainly with some of the rockets that we want to use the spaceports for, all the vertical launches, they're going to be dropping bits off. And you know, major, including wind farms. So there's quite a lot of consideration. So there are a few areas that are being looked at specifically, but the purpose of our review is to give a strategic high-level overview. So whether or not we'll actually come out with specific sites, or whether we'll come out with these are the criteria that the sites have to satisfy, I'm not sure. The other thing I want to be able to point out about the review is that although we're writing it, it's going to be edited by a formal editor appointed by the government, and then it's going to be slightly redrafted. So what I write won't necessarily come out at the end of the day as the final document. So that's just a sort of thing. So I don't know how much detail they're going to go in. It may well be that we give quite a lot of detail, and actually the government wants to hold some of that back for a second stage review. And a lot of this is an initial overview, and it requires further work. A lot of the recommendations that Pete and I have thought about are, we need a group set up to consider this particular aspect, and that would be the type of recommendation that comes out.
Two questions about the spaceport. Have you thought about offshore spaceports, and also in terms of the length of the runway, have you thought about inclines to increase the length of the runway in a short space?
Okay. 2 points on that. Firstly, for SKYLON, SKYLON is included in the report that the SSTL produced in Space Agency, and it doesn't look very good. UK is not a good place to put orbital launches unless you want to go to polar orbits. SKYLON goes anywhere. So if you were operating a SKYLON, I think you'd be barking mad to try and fly in the UK. Thank you. I hope I've just put off a customer there. The one place we've looked at and are still looking at very closely is in Kourou, at the Guyana French spaceport. And we've been there, the civil engineers have been there, we've measured up for the runway. Everyone's frightened about the runway. It is just a lump of concrete that's a bit longer than normal. The strength of runway is now often specified at really heavily used airports anyway to get runway lifetime length. So Jacobs, who are the civil engineers who build airports, they're not a bit frightened. It's just a bit more concrete at the end. It's compared with everything else we're paying for, the billions. Another 10 million for the cost of the runway is nothing. The main worry they've got is that Kourou apparently is very swampy, and they've got to know which bits of Kourou they've got to drain out and how many frogs and toads are going to be moved to do it. Mind you, we did give them a bit of a scare when we turned up to measure for the runway, I have to say.
One question from Sally, actually. It's really quick. Is the mission control going to be like a medical ICU sort of setup with for each
each passenger?
No, the way that we're looking at it is that this is an extension of the aviation field. And I think we have to look at it. These particular operations, the initial spaceplane operations, that's what it's going to be like. This is more like an aviation trip, clearly going into a much more hostile environment than it is an astronaut space trip. So the whole shift has been that we need to get a regulatory regime around it that is suitable, understanding the increased hazards that environment presents.
If you could all thank our speakers, thank you very much. Bear with us just for 1 minute while we just do a little reconfiguration then. If the panel chairs wouldn't mind coming up, we're going to have a panel session now. And David Drummond's going to help me with chairing the session. And I think we're going to try and call in one person. Okay.